That introductory video showed the morphology of the seafloor as if the water was drained away. The ocean floor is commonly thought of as very flat. Perhaps that's in part because most of us who have visited the coast see the surface as flat, and then the seafloor is flat when we wade out. However, that video showed that from a big picture perspective, there are a lot of bumps and dips. The shape of the seafloor is not homogeneous. Similarly, the distribution of the 71% of the surface that is ocean is not evenly spread across the planet. Instead, most of the oceans are in the southern hemisphere. Both the northern and southern hemispheres contain portions of three of the world's main ocean basins: the Pacific, Atlantic, and the Indian. Of these, the Pacific is the largest and deepest. The Arctic Ocean is by far the smallest and is entirely within the northern hemisphere. Some oceanographers also recognize a fifth ocean, the Southern or Antarctic Ocean. Unlike the other oceans, its distribution is not delineated by the presence of land masses. Instead, it consists of the southernmost portions of the Pacific, Atlantic, and Indian Oceans that have a different circulation pattern because of the extreme cold, dense waters in those areas. The measure of the depths of oceans is known as bathymetry, and early attempts to map the ocean floor were restricted to areas near the coast. Those wanting to map the seafloor for identifying fishing spots would tie a heavy weight to a rope or a chain and toss it over the side of the boat. Because this method only gives you the depth in one specific spot, it was a tedious job to map out even a small area. The more modern method of using sonar also has a very old origin. It was used in a very rudimentary way in the 1400s to identify boats by the long-distance travel of the sound in water. Sonar was revived in a more rigorous fashion due to the proliferation of submarines during World War I. By World War II, sonar systems could accurately determine the distance to an object by bouncing sound waves and measuring the total travel time. The modern combination of side-scan sonar and multi-beam sonar provides great resolution, but due to the immense size of the ocean, only 5% of the seafloor has been mapped this way. Therefore, when you see images of the seafloor of an entire ocean, they were created using satellites. The ocean surface is never flat, even if there are no winds or tides. And satellites can measure tiny changes in the elevation of the water surface with radar. Bumps in the ocean floor have water slightly pulled toward them due to the increased gravity from the mass of the rock. Now, this cartoon exaggerates the change in elevation. For every 1/16th of an inch rise on the water's surface, there is about a mile of rise on the seafloor causing it. Similarly, depressions on a water surface reflect dips in the seafloor. There are three major ocean provinces: continental margins, deep ocean basins, and mid-ocean ridges. Now keep in mind when you look at these profiles of the ocean floor, the slopes are exaggerated. There are two types of continental margins, and they are distinguished based on whether there is tectonic activity associated with them. Passive continental margins occur in areas like the east coast of North America, where there are very few strong earthquakes or volcanic activity. Passive margins can be further broken down into three sections. Continental shelves have all the same features you might see on the edges of continents. That's because during times of low sea levels, such as during ice ages when massive amounts of ocean water are stored in glaciers on land, the continental shelf is exposed and it experiences the same erosion and deposition as other parts of the continents. The continental slope marks the boundary between continental crust and oceanic crust, and it has a steeper slope than the continental shelf. Because of the increased slope, sediments will sometimes start to flow like an underwater landslide event. This causes scars on the continental shelf known as submarine canyons, and the sediments are deposited on the abyssal plain in the form of turbidites. Turbidites are beds of sediment where the grain size changes vertically. This is because the largest particles settle out of the sediment and water slurry first, then the medium-sized particles pile on top, and finally the smallest on top of those. Active continental margins occur where oceanic plates are subducted under continental plates. At these margins, there are still continental shelves, but the continental rises plunge continually into a trench, which marks the beginning of the deep ocean. These trenches are the deepest parts of the ocean, and because of how they form, are almost always parallel to volcanic arcs, whether those be island volcanic arcs or continental volcanic arcs. Abyssal plains make up the largest portion of the seafloor and include the flattest extensive areas on Earth. However, mantle plumes can cause underwater volcanoes called seamounts. Seamounts that break the ocean surface are volcanic islands, but they won't stick around as islands forever. As the tectonic plate that holds the volcanic islands moves away from the mantle plume, the eruptions stop and erosion takes over. The rocks also shrink as they continue to cool over millions of years, and eventually the volcanic island has its top portion flattened by waves, and cooling lowers it below the sea surface. The remnant is called a geo. Now, this process also explains how coral atolls form. Corals continue to grow up as the seamount is eroded and shrinks down. Oceanic ridges are the third region in the deep ocean, and they are broad regions of raised, rugged seafloor. A rift valley lies in the middle of ocean ridges, and that's where all the action is happening. Rocks there are being pulled apart, forming normal faults that allow for the upflow of molten material. There are three major categories of sediments being deposited on the seafloor, differing by where they come from. Terrigenous sediment comes from land and includes particles washed in by rivers and blown in by wind. This image shows the coast of Africa and southwest Europe, and the dust from the Sahara being lifted into the Atlantic Ocean. Biogenous sediments are the resistant pieces of dead stuff, mainly the skeletons of microscopic animals and algae. There are two types of biogenous sediment that are far more common than others. Calcareous ooze has the composition of calcite and is formed primarily from coccoliths, shown in the upper left. Diatoms in the lower right create siliceous ooze, which has the composition of quartz. Hydrogenous sediments crystallize directly from seawater. The example shown here is a type of hydrothermic vent known as a black smoker. These can appear rather quickly and rapidly form large accumulation of metals, especially irons, nickels, and silvers. Even though hydrothermal vents create deposits dense with valuable metals, there are not very many of them. Therefore, there is more economic incentive to mine the much more extensive manganese deposits of the deep ocean. However, while it's possible, it's not yet profitable to mine at those depths. Closer to land, sand is commonly mined for beach rejuvenation and construction materials. Ocean water contains table salt that can be precipitated by evaporating the water. Well, technically, there are also massive quantities of many precious metals in seawater that could be mined by precipitating out from the solution. But the density of those metals are tiny. Therefore, it would take massive amounts of seawater to create an economically useful amount of metals. The highest value physical commodities taken from the ocean are oil and natural gas pumped from under the seafloor. Now, there is another possible resource associated with those: gas hydrates. These are molecules of natural gases encased in water molecules. They form in areas that are very cold and under high pressure, and deep ocean sediments are perfect for that. The amount of energy contained in gas hydrates is more than all other fossil fuels combined. However, they are not stable at the surface, and in fact, they can cause explosions when drilling for oil and conventional natural gas as the drill depressurizes the sediment.